There are a couple other situations where substitutions can help us solve a differential equation. So here's one of them. We're going to solve dy dx equals 1 plus x plus y over x plus y. Now when you see this differential equation, what I hope occurs to you is that x plus y shows up in two places. And whenever you have a situation where there's some expression, x plus y in this case, that shows up in more than one place, it's often nice to give that expression a name. So we're going to introduce a new variable u, and it's just our name for x plus y. Of course, now that we've introduced a new variable, we have to figure out how du dx is related to dy dx. So we need to differentiate both sides. So du dx, and remember the multivariable chain rule, it's partial the derivative of u with the derivative of this formula with respect to x times dx dx plus the derivative of our substitution formula with respect to y times dy dx. So du dx, let's see, the derivative of this with respect to x, well, the y term goes away because remember we're treating y like a constant as we take this derivative. And the derivative of x is just 1 times dx dx, that's also 1, plus derivative of this formula with respect to y, well, that's 1 because we're treating x like a constant, so the x term goes away, and the derivative of y with respect to y is just 1 times dy dx. Okay, so what we get here is that du dx is 1 plus dy dx. And that means that dy dx is du dx minus 1. Okay, so now we have our substitution formulas, right? And this one, I guess, we can rearrange y equals u minus x if we need to, but we actually won't need that. We have these substitution equations here and here. So we can use this to rewrite our differential equation. Now on the left-hand side, dy dx, we found that that's du dx minus 1 equals, and then on the right-hand side, we have 1 plus x plus y, that's u, over x plus y, that's also u. Okay, so now this, we can simplify this. This is, I guess, 1 over u plus 1. And then, I guess, add 1 to both sides. Du dx is equal to 1 over u plus 2. Okay, now this is a separable equation. So at this point, we could finish solving this, but at this point, let's just declare victory and acknowledge that we could finish solving this if we needed to. So in this situation, right, what happened is we had some nice expression that showed up more than once, and so that's what we chose for our substitution. This often happens when you have some linear combination of x and y. So if you have some expression that looks like, say, some number times x plus some number times y, maybe even plus some other number, often this is a good thing to take for you if an expression like this shows up in your differential equation. Let's look at a couple other examples. So how about this one? X times e to the y times y prime minus 2 times e to the y equals x squared. So this is extremely nonlinear, right? Not separable either. So this is a real mess. But since e to the y shows up in two places, it sort of makes you think, maybe that would be a good choice for a substitution. So let's take u to be e to the y. Now we need to find du dx. So we need the derivative of e to the y, that's e to the y, but then the chain rule says we have to multiply by the derivative of y with respect to x. And so here's our substitution equation, right? So now let's go ahead and convert our differential equations to u's instead of y's. So we get x times e to the y times y prime. According to this second substitution equation, that's just du dx. Okay, minus 2 times e to the y, but e to the y is just u, so that's 2 times u equals x squared. And now that we have it written this way, the resulting equation is linear, and we know how to solve linear equations. So again, if you want to know how this works out, you feel free to finish solving this differential equation, but since we know how to solve linear equations, in principle, this is solved. So here's another example. We're going to solve x times sine of y times dy dx plus cosine of y equals minus x squared e to the x. So again, this differential equation is strongly nonlinear because our unknown function y is trapped inside of some trig functions. But if you look carefully, this part right here is actually just the derivative of this part right here. Right? Cosine of y, if we take the derivative of that with respect to x, we get sine of y, well, up to a minus sign. But also the chain rule would spit out dy dx. So it seems like maybe what we should do is take u to be cosine of y. So with this idea for a substitution, we can differentiate both sides. So du dx is, so we're going to differentiate this. We get minus sine of y, but then the chain rule says we have to multiply by the derivative of y with respect to x. Okay, and yeah, sure enough, here's our sine of y times dy dx. Let's get this minus sign to the other side, because that's how we're going to use it in this when we do the substitution. All right, so now we can do our substitution. We get x times sine of y times dy dx, but now we know that that is minus du dx plus cosine y, but that's u, equals minus x squared e to the x. So now this differential equation is minus x du dx plus u equals minus x squared e to the x. And look, again, this substitution has turned an extremely nonlinear equation into a linear equation. And so in principle, we could solve this, find u, and then undo the substitution to find y.